And with that, this is Chris Parker of Marine Weather Center. This is Weather 100 Basic Weather. This is the first of a series of 12, and we'll be streaming them on the internet. You'll be getting the details. We'll keep you in contact with this, and you'll be invited to the next ones as they go. And Chris, with that, I'm going to turn it over to you.
All right. Thank you very much, Joan, and good evening, everyone. Um, we will, if anyone has any questions, I've got the chat window open so I can see any questions if you have those as we go through. Um, this will be about an hour, maybe an hour and a half at the most. And um, first, I'll do a little introduction about me. I started sailing when I was about 10 years old. My dad bought a powerboat in New Jersey. We took it to the Chesapeake Bay, spent a couple years on that, went to summer camp and learned to sail. And once I got the sailing bug, um, I have been sailing and powerboating ever since. And that's going on 50 years. We bought Dragon Lady pictured here in 1993 after Hurricane Andrew in Miami and refitted her and sailed her up and down the US East Coast, Bahamas. We were going to go sailing around the world on Dragon Lady, the Choi Lee 30, but she was pretty heavily laden. So notice that she's sitting kind of low on her waterline. The previous owners had raised the waterline. We raised the waterline again, and she was still right on her waterline. So we had solar panels, wind generator, radar. We put a bowsprit on and a self-steering gear on the stern. And Michael's a sailmaker, so we had like a dozen sails for all sorts of conditions. And so she was, really too overloaded to be safe sailing around the world. But she was really fun for up and down the U.S. East Coast and in the Bahamas. My husband Michael, Wizard the cat. Wizard was with us for uh, I guess about 7 of the years we were on the boat, and he preferred being a house cat, but he was a good boat cat. Definitely have uh, kids and pets on board. They're fantastic. They adapt way better than we would expect. When we were in the Bahamas in 2002, we saw this boat and fell in love with her, Morgan 34, and we bought her, refitted her, and sailed her in Bahamas, up and down US East Coast, and offshore to Bermuda, offshore to the Caribbean, nonstop from the Bahamas. And she was a fantastic sailing boat. We still have her. She's been on the hard for about 20 years. And we're in the process of refitting her again. Going to go sailing on her part-time beginning probably next winter, not this coming winter, but the following. So I've done, a bunch of offshore sailing, sailed to Bermuda 3 times, once on Bellamy or Morgan 34, once on my uncle's Pacific Seacraft 34 or 37. I guess she was a Pacific Seacraft 37. And then on a 200-foot plus sailing ship replica, did a weather instruction course on that from Fort Lauderdale to Bermuda back about 10 years or so ago. Don't know if how many folks have single sideband radio, but we do operate on single sideband as well as Zoom morning and evening sessions. I'll explain that in a moment. Right now, our radio antenna is down, but we're in the process of effecting repairs, and hopefully we'll have that up this fall. Um, so I'm a weather expert. And Stormy, Sean, Laura, and Matthew are all meteorologists working with us. We help people get to their destination safely and enjoy their time in paradise after they arrive. And that makes us kind of unique. A lot of forecasting outfits just get you from point A to point B. And we realize that once you arrive at your destination, you still need weather forecasts that are maybe somewhat different and tweaked for cruisers. been forecasting weather and routing vessels for 23 years. I've been interested in weather since I was 4 years old. Always wanted to be a TV meteorologist. I studied weather in college for 2 years, but there was way too much physics and calculus. So I actually have a degree in business administration from a different college. Um, I started forecasting for our own use in the Bahamas in January 2000. And, the cruising community, we talked to each other, and, someone would ask us what we were going to do next day or the day after. And we'd say, well, we're going to do this. And they'd ask why. And Michael would say, well, Chris thinks it's going to do such and such with the weather. And I was right more often than not, and more often than any other forecasts. So all of our friends started asking us for what was going to go on with the weather, and it just kind of turned into a business. And then I teamed up with Caribbean Weather Center, David Jones' old outfit, after he passed away, and we renamed it Marine Weather Center in 2011. I'm also a hang glider pilot, and I learned a lot about weather, hang gliding, and sailing, much more so than in the classroom. My experience is on small boats. I get seasick, and I started with a fear of everything. So, what makes us unique at Marine Weather Center? Our forecasts are by someone who's spent time on a small boat. All of our meteorologists are familiar with small boats and have spent time on them, and they're geared to someone on a small boat, sailboat, or powerboat. Forecasts include the worst plausible solution, not just the most likely solution. And our goal is for you not to have any unpleasant surprises. And the definition of an unpleasant surprise is going to vary from person to person. The forecast products we provide, three distinct products: custom forecasts, worldwide coverage, 365 days a year. Those are delivered by email, telephone, text message. They're created just for your vessel and itinerary. The cost is $40 to $100 per forecast, depending on the length of the forecast and how long we're working with you before departure to find a weather window, or $330 for a package of 10 custom forecast credits, good for a year. We also have webcasts that are simulcast with the single sideband nets. Obviously, the single sideband nets aren't worldwide. They're just within a couple thousand miles of Florida. But the webcasts, we have worldwide coverage 2 times a day, mornings and evenings, daily except Sundays. And the cost of that's $230 a year or $125 a month. And then regional daily email forecasts. We provide the information you need to make your own weather-based decisions. And we do that for the East Caribbean, West Caribbean, Bahamas, Florida, and US East Coast. That's $230 a year. And we also can do monthly or a number of months. Most folks combine webcasts with the regional email forecasts, $350 a year. And most clients purchase some sort of a combo of 2 or 3 of our services. So what are we getting together to discuss? What are we hoping to learn? It's important to appreciate that weather is really important. It's mission critical sometimes. And lots can go wrong on a boat. You can have bad fuel. We had a client today, they took on bad fuel in Charleston, had to turn back. So you can have bad fuel, a seasick crew, broken gear, a through-hull fitting fails, a rudder fails, et cetera, et cetera. Things are much more likely to go wrong on board, gear failures, crew failures, when the weather is bad. And not only are you more likely to have bad things happen when the weather is bad, but they're tougher to fix. So we want to try to avoid bad weather to try to minimize damage to the vessel and the crew. And so you don't have tough to fix things when the weather is bad. Weather is part science and part art. Conditions often deviate from a forecast, and it's really important for you to understand why. Why is the weather doing what it's doing so that you know how to anticipate what's coming next? So, if the forecast is for southwest at 15 knots and it turns into southwest at 25 knots unexpectedly, If you know that there's a cold front coming and you know that the cold front's going to pass you in about 3 hours, you know that at least these conditions aren't going to last for more than about 3 hours before the weather's going to change. So important to know not only what's going to happen, but why it's going to happen so that when things deviate from the forecast, you can anticipate what's going to happen next, even if it's somewhat different from the forecast. Obviously, avoiding inclement weather is best, but when this isn't possible, we try to minimize the inclement weather, and knowing what's coming allows you to prepare more effectively. To the extent possible, you want to start your voyage with an expectation of favorable weather. And when the expectation of inclement weather is the lowest. We coach clients, and Delta Airlines, I know, does this, to be situationally aware and understand what's likely to happen next regarding the weather, regarding other things on board. You have a game plan in your mind for how things are going to evolve, what issues you're going to have to address. You should know before you even leave the dock when you're probably going to have to change course, tack, jibe, change sail plan, tuck in a reef, shake out a reef, when you're going to have to have the crew mustered and ready for action and well rested and well fed. So if you've got a couple of days of nice weather, you're going to want to make sure that the crew is well rested and well fed if you know that there's bad weather coming up so that you're prepared for it when it comes. So you want to identify the inflection points in the weather forecast when the weather is going to change, and the decision points along your journey when you're going to have to make a weather-based decision. And if you know that, and you know all the other things that are going on board throughout the trip, and you have a game plan, then when something inevitably happens that you're not expecting, you can turn all of your attention to that thing because everything else is on autopilot. You know what the weather's doing, you know when you're probably going to have to change sail plan. Um, your crew is well rested, you're fully prepared, and when the proverbial stuff hits the fan, you can focus all of your attention just on solving the problem at hand, and everything else is taken care of and on autopilot. You also want to obtain an updated weather forecast prior to any weather-based decision that you're going to have to make. When you approach the weather, you want to approach it by asking a number of questions. What are the large-scale weather features? Is there a low pressure system coming, a high pressure system, a cold front, a trough, a warm front? Is there any land-induced weather? Is there a coastline effect, a cape effect, any sort of terrain effect that's going to impact the weather? Are there sea surface currents, either tidal currents or geostrophic currents, which are non-tidal currents, like the Gulf Stream? Is there going to be precipitation? Will the precipitation impact the wind and the seas? Will there be lightning? Is it generally a lifting air mass or a sinking air mass? We're going to touch on all of these points in the next 12 modules so that you understand why these questions are important and what the answers mean. Is there going to be limited visibility? What are the trends in the weather? Is the weather improving or deteriorating? When are the inflection points in the weather? When is the weather going to change? So after the above assessment, you know whether to trust the forecast or not, what could go wrong with the weather, and you can develop a plan to avoid or manage any inclement weather. So these are the modules we're going to discuss tonight. We'll discuss energy transfer and basic concepts, and this is an introduction to weather. And then And on Thursday night, July 30, we'll discuss large scale weather systems, high pressure systems, low pressure system, cold fronts, things like that. The third session is how upper air weather influences the surface. I spent a long time trying to figure out why we would need to know what's going on at 500 millibars, because the surface forecast already includes what's going on at 500 millibars. That's in part what creates the surface forecast. So why do I need to know what's going on at 500 millibars? Well, the answer is that that can help me understand why things are happening. It doesn't change what's going to happen because that's already baked into the forecast, but it helps add depth to my understanding of why things are happening so that I can anticipate what might happen next if the weather doesn't evolve exactly the way we're expecting. We'll explore the importance of lift, convection, and thermodynamics. We're actually going to talk about what a millibar is tonight. So what a barometer is and what a millibar is, we're going to talk about that tonight. That's one of the introduction topics. Uh, then we'll discuss in Weather 202 small scale weather events and how to anticipate them. We'll spend 2 sessions on numerical or computer generated forecasts, how they're created, their strengths, weaknesses, and using them. And then we'll get into Weather 301, which is winds, which is waves and seas, what drives the waves, their behavior, their impacts on the vessel, what happens when there's current involved, sea surface currents or tidal currents. A really interesting module is, well, they're all interesting, I hope, but one that you might not think would be necessary, but weather routing. What does a weather router do? How do they do it? And how to think like a weather router and when to use one. So, well, I can coach you about how to think like a weather router, and that will, I don't think you'll replace a weather router because, we do this every day. Practice makes perfect. We help thousands of vessels a year on passage, and that sort of practice kind of refines the craft. But the more you know about how a weather router thinks, the more you can think like one, the better your result will be, and the easier our jobs will be. Then we'll get into 2 sessions where we discuss specific forecast resources on the internet, via browser and via apps, and then creating a forecast and using a forecast for your own boat. So the main points we'll discuss tonight are weather being Earth's mechanism to redistribute atmospheric energy. And if you're ever unsure about why things are happening, try to figure out where the energy is in the problem. Because the reason weather occurs is because the Earth's energy is not distributed evenly. We'll discuss that in a few minutes. And weather is the mechanism by which Earth seeks to equalize atmospheric energy. Warm air rises, moisture has latent or potential energy. Air moves horizontally in addition to vertically. Energy equalization occurs on many different scales, the micro scale, the large scale, and the global, the synoptic scale and the global scale. We'll explore in detail the really big picture, global energy transfer. And we'll introduce some small scale energy transfer, but much more on that in modules 201 and 202. So jumping into the meat of the discussion. Weather is the atmosphere's mechanism to equalize energy. What energy are we talking about? Radiation from the sun. A second type of energy is sensible heat, heat that you can feel, sensible heat. That's the portion of radiation from the sun that gets absorbed by the surface of the water, the surface of the land, your skin, sensible heat. And then there's latent heat. And we're going to talk a lot about latent heat tonight. Water vapor releases latent heat when there's a state change from gas to water, and even more latent heat gets released when there's a state change from water to ice. And that has really important ramifications for developing thunderstorms. And we'll explain that mechanism tonight. So we just learned the three types of energy that need to be equalized in the atmosphere: radiation from the sun, sensible heat, and latent heat. This energy is redistributed primarily by three mechanisms. I don't really like, or I really dislike big fancy words that are not in our normal vocabulary, because what I find is that when I use a big fancy word like advection, I have to spend most of my mental energy trying to figure out what the word advection means, and I don't have a lot of mental energy left to understand the concept. So I'm using that fancy word here, but I'll explain how to think about it. So forget that I'm using the term advection. That's the technically accurate word for it, but it's basically just the wind blowing. So the wind is going to blow from one place to the other, and that moves air of different energy states. Advection is simply the wind blowing, the motion of air. The second mechanism is convection. Convection relates to heat, heating or cooling, and that's air of different temperature characteristics moving up or down in the atmosphere. The third mechanism is conduction, and that's the molecule to molecule transfer of heat from adjacent molecules. When you touch your finger to a stove burner, um, it's conduction that's burning your finger. There is heat that's conducted from the stove surface up into your finger, and that's what burns your finger. So conduction, molecule to molecule transfer. So let's illustrate how weather equalizes energy with an example familiar to everyone, the Seabreeze convection cycle. We'll do that in a second. But first, I want to talk about a term that you'll want to understand, that's albedo. And albedo refers to the property of reflectivity versus absorption of the surface of an object. So you probably realize that dark surfaces get hotter in the sun than light surfaces. The reason is that different colors have different properties of solar reflectivity versus absorption, and that term is called albedo. Pure white snow has an albedo of about 0.9. It reflects 90% of solar radiation and only absorbs 10% of incoming solar radiation. Ice is about albedo of 0.6. It reflects 60% of solar radiation. White sand on a beach has an albedo of about 0.3. It reflects about 30% of solar radiation, but it absorbs 70%. And then black asphalt has an albedo of only 0.04. It only reflects 4% of incoming solar radiation. It absorbs 96% as sensible heat. We're going to mention conduction more in a couple of minutes, but the reason, let's say, the sea surface and other wet surfaces tend to be cooler than dry surfaces in the sun is the water conducts heat away from the surface down into the substrate. So here we have a picture of a white sandy beach with an albedo of about 0.3. That is reflecting 30% of incoming solar radiation, absorbing 70% that turns into sensible heat, versus a blacktop parking lot with an albedo of 0.04, and that is absorbing 96% of incoming solar radiation. Gets really, really hot. So now our land breeze sea breeze cycle. And we're going to talk specifically first about the sea breeze convection cycle. And this answers the question, why does weather occur? It's redistributing unevenly distributed energy. So the concept here is convection, air of differing energy levels, different heat levels, moving up or down in the atmosphere based on their thermal properties. So let's say that I drive down to the beach at 8 o'clock in the morning, put my beach towel down, maybe a beach chair, get out a book, start reading, and it gets to be, 11 o'clock, and I'm getting kind of thirsty for a beer. And so I get up from my beach chair and start walking down the beach, and I realize that I left my wallet in the car, and it's in the parking lot. So the beach is really hot beneath my feet, and it's kind of uncomfortable because the sun's been beating down on the beach for a couple hours and the sand is pretty hot. But when I get to and by the way, I hate shoes. So I don't have shoes on. I'm in my bare feet. So I get to the parking lot, and the parking lot just had the blacktop redone. So it's a really, really dark black parking lot. And when I hit that blacktop parking lot, I start running to my car because the soles of my feet are about to burn off because it is so hot. Well, what do you think happens to the air that is right above the parking lot? It gets heated to a higher temperature than the surrounding air. So all the air over land is tending to warm as we go through the day. It's all buoyant. It's all generally rising. But particularly the air over the blacktop parking lot is going to rise first and fastest because it's the hottest. So we've got columns of air moving up, particularly from the blacktop parking lots. And that air moving up displaces air molecules that were already in the atmosphere over the parking lot and over the land in general. Some of that air that was displaced is going to be forced out over the water. Remember, the air is generally buoyant all over the land because the land is generally all heating up during the day. So the air that was over the land is going to get forced out over the water. So some of the air molecules that were over the water to start with are going to get forced downward. And the air molecules that were over the water are going to get sucked into the beach to replace the air that rose over the parking lots and the beach and the farmlands and generally over the land areas. That is the sea breeze convection cycle, and that tends to be self-reinforcing. It gets stronger and stronger as we go through the afternoon until the sun is no longer heating the surface a lot. So 5, 6, 7 o'clock, that starts winding down and going more neutral, and the sea breeze convection cycle usually stops sometime, roughly around sunset. This is another graphic. During daytime, we tend to get warm air rising over land and being forced out, forcing air that was over land out over the water, and that forces air downward, and then some of that air gets sucked inward to the beach to replace the air that moved upward. At night, the reverse happens. At night, the land cools down a lot, and the air over the land cools down more so than the air over the water because the water stays relatively warmer at night. The temperature of the surface of the water may vary by a degree or two between the afternoon and the morning, but the temperature of the land may vary by, the temperature of the air over the land may vary by 10, 20, 30 degrees between day and night. The land itself may vary by 50, 60 degrees, 70 degrees. You could almost fry an egg on a blacktop parking lot in the middle of the summer. You probably could. But at night, it cools down quite a bit, cooler generally than the sea surface. So at night, we tend to get air sinking over land, air rising over water, and air getting sucked from the land to the water to replace the air that rose over the water. We're going to talk in a few minutes about um, air having momentum. It's got weight and momentum and inertia. And usually the land breeze sea breeze cycle lags behind what you would expect. So typically we'll get the land breeze peaking between about dawn and maybe 9 or 10 in the morning. And then after that, we start shifting to neutral and then a sea breeze. And the sea breeze typically peaks in the late afternoon and starts shutting down towards sunset. But there's a little bit of a lag. You might expect the sea breeze to peak when the sun is highest in the air and heating the ground to the greatest extent. But it takes time. The air has momentum, and it takes time to reverse that momentum and slow things down again. So we tend to see the strongest sea breeze in the late afternoon and the strongest land breeze in the late overnight hours. And Andrew, you asked, why does the hot air move out over the water, not just keep moving upward? So the air generally is going to cool as it rises in the atmosphere. One of the properties of a gas is that when the pressure drops, the temperature drops. And we'll see tonight why the pressure is going to drop as you go up in the atmosphere. And that's going to cause a temperature drop. So the air is generally cooling with altitude. Um, Air is only going to keep rising if it's warmer than the surrounding air mass. And eventually the air mass is going to equalize and kind of stop rising. But the air parcels that are rising, they can't go up beyond the troposphere, beyond the area where weather occurs on Earth. So they get forced out, horizontally rather than just keeping rising. And there's also some sucking effect. So we get the sucking of the air from over the water to replace the air that rose over the land. And that helps to suck down the air in the column above the water. And that helps to suck out the air from over the land. So it's a combination of pushing and pulling. So during the day, we've got pushing from the surface upward, and we've got pulling from the ocean inward. And both of those things cause or help to cause the air that's rising to eventually get sucked out and sucked down and then pulled in. So it's push, and it's a combination of push and pull, and then mostly pull, and then all pull. So push, push and pull, and then pull. Okay. So a little bit more about the latent or potential heat and why it's important. Hot air rises, that's convection that transports energy in the form of sensible heat, hot air rising, and latent heat, which is the potential heat that's in water vapor that rises. It transports that upward in the atmosphere. Hot air rises due to convection, and that transports energy upward in the atmosphere. As that air cools with altitude, some of the water vapor may condense into water droplets that releases heat, and that makes the parcel of air that's rising even warmer and moves it even faster and higher up into the atmosphere and can create towering thunderstorms. So let's examine a parcel of air early in the morning. So this is a picture, sun is just coming up. We're identifying a parcel of air, a group of air molecules, and we've got those in, let's say, a small container, a balloon, any sort of a small container. And we're going to keep examining just these air molecules. Early in the morning, those molecules are relatively cool. They're in a relatively compact space. They're in a low energy state. The water is all in vapor form, so you can't see it unless maybe it's foggy and then there's some water droplets. As the morning progresses, the sun heats the ground unevenly, creating some parcels of air that are warmer than the surrounding air mass, and those parcels start rising. Molecules in our warmer parcels are bouncing around more actively. They're expanding. They're in a higher energy state, and they're rising. The parcels which are warmer than the surrounding air mass rise, and that's called convection. And the water is still all in vapor form, so you can't see it unless it happens to be a little foggy. So as our warm air parcel keeps rising, it cools down because of one of the properties of gas. As the pressure drops, the gas cools. The parcel of air is going to cool. All of the air in the surrounding air mass, though, is cooling as well. And so our parcel of air will keep rising as long as it's warmer than the surrounding environment. At some point, the parcel may get so cool that it can no longer hold all the water in vapor form. And that water vapor starts condensing out into water droplets, and that forms visible clouds. That process is an exothermic reaction. It releases latent heat, the potential heat that's in the water vapor, into our parcel of air, making our parcel of air even hotter relative to the surrounding environment. And that parcel of air is going to keep rising even faster. Now, at some point, the air is going to condense out all the moisture it can. The the humidity level, the water vapor level drops, so that even though the air is cooling, there's just not enough available moisture. It's not super saturated anymore, and it stops condensing out water vapor. And at that point, we get the top of a cloud because the air is not really rising too much anymore, and air can start coming crashing down. What goes up must come down. And the more we force air upwards due to the latent heat release, the more we get towering thunderstorms. And when that air comes crashing down from 50,000 feet, it often does so with a vengeance. The vertical speed of rising air is usually on the order of a couple of miles an hour, maybe 5 or 10 miles an hour at the most. But sinking air can be coming down at 100 miles an hour. So the air can sink much faster than it rises. So I notice, is this working? I don't think that link is working. Oh, it is. Okay. So I'm going to slow this down and play it again. So This is latent heat input. I misspelled that. Heat, latent heat input. We start with water in a pot on a stove. When we input heat into the water, if we input enough heat into the water is going to reach a boiling point, and some of that water is going to transform into water vapor. It's going to go from liquid water to invisible water vapor. And that is evaporation, that's endothermic, that requires heat from the outside. And all that heat that we put into it is latent heat that has the potential to come out of that water vapor when we transform it back from a gas into a liquid, into water droplets and raindrops. So imagine all that heat that it takes to boil the water to shift from a liquid to a gas. All that heat is latent heat, potential energy that is ready and willing to come out of the air when we transform it back from a gas to a liquid water. And Rich, yes, there will be a recording available. Yep.
Yes, there will be a recording available. Nicole, are you still there?
Yes, I'm here.
Hopefully. Okay, Nicole, I am in a tornado warning.
Okay,
They told us to take cover, so if I disappear, please continue and record.
will do.
Okay. And so latent heat output, let's start with a moist atmosphere and remove heat from the moist air that's in contact with something cooler, in this case, a beer bottle. When enough heat has been removed, the air becomes supersaturated and we get water droplets, water drops forming on our cool beer bottle. So this is the reverse process. This releases heat as it transforms from invisible water vapor into visible water drops. So remember, weather is their mechanism to equalize energy. Hot and often moist air rises, energy moves up in the atmosphere. That's convection. Some air molecules, some energy jumps from molecule to molecule. That's conduction. And then wind blows different energy levels around, and that's advection. So let's talk about incoming solar radiation a little bit, deeper dive into that. We've got 100% of incoming solar radiation during the day. Some of it's absorbed by things in the atmosphere that are not clouds. Some are absorbed by clouds. Some are reflected by clouds. These are the percentages of the incoming solar radiation that are absorbed or reflected, and a lot of it's absorbed by the surface of the Earth. We also have outgoing radiation even during the day. There's sensible and latent heat transfer, emissions from clouds, things like that. So there's an outgoing radiation budget as well. And then at night, obviously, there's no incoming radiation at night, but at night we have outgoing radiational cooling. On a clear night, we get a lot of radiation projecting out into space. When there are clouds, that acts like a blanket, and we get less radiation outward into space. So there's some really cool graphics from the European Met Office that we'll discuss. And this is one of them. This is the annual net incoming surface solar radiation. That's a lot of words. What it means is, and this is the color scale over here, from almost none to a lot. We go from green to yellow to orange. And areas that are shaded in green do not have much net incoming surface solar radiation. Not much of the sun's energy gets to the ground near the North Pole or the South Pole. As we move toward the equator, we get more and more air, more and more incoming solar radiation making it to the surface on a mean annual average basis. And something interesting happens near the equator, and this tends to be near and within about 10 degrees north of the equator. And there's the intertropical convergence zone. We'll talk about that in a little bit. And for reasons we'll explain in a little bit, that causes less incoming solar radiation to reach the Earth's surface. So there's less filtering of the atmosphere near the poles. I'm sorry, there's less filtering of the atmosphere near the equator versus near the poles. The sun has to go through a lot more atmosphere because it goes through the atmosphere obliquely at an oblique angle toward the poles. And the sun beats down much more directly toward the equator and within maybe 30 degrees north and south of the equator. There are more clouds in the ITCZ, and that reduces the incoming solar radiation near the equator. And there are fewer clouds during daylight hours over marine areas than there are over land, because the sea surface does not heat up as much during the day as the land does. And so that supports much more cloud development over the land versus over the sea. So you can see that over land masses like South America, even at a similar latitude, there's less incoming solar radiation over land than there is over the sea. This next graphic divides winter and summer. So you can see that in winter in the Northern Hemisphere, there is zero incoming solar radiation north of about 60 degrees north latitude because it's just dark all year round, or for a couple of months. And as we move south, we get more and more radiation, but by far there's more incoming solar radiation in the Southern Hemisphere than in the Northern Hemisphere in our winter. The reverse is true in our summer. Areas south of about 60 degrees south latitude see absolutely zero incoming solar radiation. But as we move toward the equator, we get more and more. But in the Northern Hemisphere, there's far more than in the Southern Hemisphere in our summer. This is another way to look at the latent heat energy cycle. We get evaporation from the surface. We get transpiration from trees. There's condensation at altitude. There's precipitation. There's runoff that replenishes the watershed. It takes energy to make this evaporation and transpiration and air rising, and it releases energy when we get precipitation. So let's talk about the moisture budget. This is the net annual evaporation minus precipitation. So this is the net annual evaporation cycle. And when you think moisture evaporation, you want to be thinking latent heat energy. This is all potential energy that's going up in the atmosphere. So we get the greatest annual net evaporation when we have the yellows and the oranges. You can see that over the sea, there tends to be much more evaporation than over the land. Obviously, there's a lot more water to be evaporated over the sea than versus over the land. So most of that evaporation occurs between the equator and 30 south and between about 10 and 40 north, with the areas between the equator and 10 degrees north in the intertropical convergence zone where there's a lot of precipitation. So there's a lot of evaporation there too, but there's even more precipitation. So the areas near the equator are actually in a deficit for evaporation. They get more precipitation than they do of the evaporation. The same is true in the very upper latitudes. There's not a lot of precipitation in the upper latitudes, but there's even less evaporation. There's so little heat energy, so little incoming solar radiation, that there's just not much evaporation at the upper latitudes. So you can see that's pretty clear that that's an uneven distribution of energy. Could you make it more uneven than that? It is tremendously uneven, and weather has to occur to try to equalize that energy. So weather occurs because of unevenly distributed energy, radiation energy from the sun, and uneven radiational cooling out into space. Weather is Earth's mechanism to try to equalize that energy. It does it by having relatively warmer air rise, convection. And if it rises enough, it begins condensing water vapor into water droplets. That releases the latent heat that's in the atmosphere in that water vapor, typically high in the atmosphere. And then the less energetic cool air that's cooler and more dense sinks to the earth, and that cycle repeats. Also, especially on wet surfaces like oceans, lakes, wet ground, there's a lot of conduction that transports energy into the substrate, into the body of water, or into the wet land. And there's air mass movement that through advection, through the blowing of wind, moves the energy around. And we're going to talk about that more in Module 101 on Thursday night. So, little quiz time. True or false? Earth is heated and cooled unevenly. Obviously, that's true. Weather is Earth's mechanism to redistribute heat, drive wind, equalize energy, or none of the above. So, maybe a couple of those answers could be correct, but the most correct answer is weather is Earth's mechanism to equalize energy. And I'll get to a couple of questions after we finish the little quiz. Warm air, air that's warmer than the surrounding environment, does it rise or fall? Warm air that's warmer than its surrounding environment is going to rise. Moisture. Does moisture contain latent heat? Moisture can be water, vapor, or solid. Moisture can form into clouds, or all the above. All the above is the most correct. Moisture does all of those. Which of the following is true? When moist air is cooled, when the heat energy is removed, water vapor converts into water droplets, forming visible clouds. This process is exothermic, and it releases heat into the air parcel where that condensation occurred. Is that statement true, or is the following statement true? When moist air is warmed, when heat energy is added, the water vapor converts into water droplets, forming clouds. That process is endothermic and releases heat into the air parcel. So the second statement has a couple of things wrong with it. The first statement is correct. So John McReynolds, sea breeze versus offshore wind, advection versus conduction. So advection is generally the large scale synoptic, high pressure here, low pressure there. We're going to get over an area of hundreds or thousands of miles advection, air moving on a large scale. Conduction is molecule to molecule movement of energy, and convection is localized. A parcel of air that's warmer is going to rise, if it's warmer than the surrounding environment. A parcel of air that's cooler than the surrounding environment is going to fall. And sea breeze versus offshore wind. So offshore wind is generally supported by the large scale pressure gradient. High pressure here, low pressure 1,000 miles away. That's what typically supports offshore wind, other than convective squalls and thunderstorms. The land breeze sea breeze cycle tends to occur within a certain distance from land. If the land mass is small, then the land breeze sea breeze cycle may be pretty subtle and may only exist for a couple of miles away from the land. If the land mass is really big, then the land breeze sea breeze can be very significant and it can stretch 100 miles out to sea. So that's a little bit more on sea breeze versus offshore wind. A little deeper on why things are different from 0 to 10 degrees north latitude. So we're going to come back to that and address that when we talk about the global energy transfer, and I'll talk a little bit more about the intertropical convergence zone. But the reason is from 0 to 10 degrees north latitude, we have the intertropical convergence zone where the northern and southern hemisphere winds come together, and that creates a lot of cloud cover and a lot of squally weather. And that's where a lot of tropical systems start, kind of at the northern edge of that, or in the southern hemisphere, the southern edge of that. And so there's a lot of cloud cover and a lot of precipitation and not a lot of sunshine. So the movement of hot or cold water via ocean currents that would be advection. So that's the large scale movement. Like if you're talking about the Gulf Stream, the Gulf Stream would be ocean advection of water, large scale movement of water. And the sea breeze is going to give you an onshore wind blowing toward the land. So a sea breeze is going to be air that's over the water getting sucked into the land. And a land breeze is the opposite, air that was over the land getting sucked out into the water. Okay, so part 2 of 3, we'll talk about a couple of different topics. One is the barometer, and this gets into the weight of the atmosphere. We'll talk a little bit about how and why that's important. This middle section is going to go pretty quickly, and then the third section is global energy transfer, and we'll spend a few minutes more talking about that. So what is a barometer? A barometer is simply a scale. Think of it like your bathroom scale. It measures the weight of all the air molecules above it in the column of air. And jumping down to the last little tidbit here, the air molecules in a column of air, let's say we've got a bathroom scale that's exactly 1 foot by 1 foot, and it's sitting on the surface at sea level. And the bathroom scale, again, measures 1 foot by 1 foot. If you took that bathroom scale and put it in space where there are no air molecules at all, and zeroed the scale out, set it to 0 in space where there's no air molecules at all, and then you brought that bathroom scale back to sea level and put it on the ground at sea level and didn't reset it. So it's set to measure the weight of space, which has no weight. The bathroom scale is going to read the same weight as a column of mercury that's 1 foot by 1 foot by 30 inches high. So that's a tremendous amount of weight. And so it's measuring the weight of all the air molecules from the surface up to the upper levels of the atmosphere, 100 or even hundreds of miles above the Earth's surface. Now, there aren't very many air molecules above about 100 miles up. So for all intents and purposes, it's measuring the weight of the atmosphere in the first roughly 100 miles of the atmosphere. Air consists of molecules of oxygen, hydrogen, carbon, nitrogen, and trace gases, often in the form of CO2, carbon dioxide, or H2O, water. Molecules have weight, and when they move, they have momentum. They have inertia, which means they don't want to move unless some force acts on them to make them move. And once they're moving, they have momentum. They don't want to stop unless something acts on them to make them stop. A barometer reads the weight of the molecules in the column of air above the scale, from the surface of the Earth at sea level to 100 miles up. And the standard atmosphere weighs the same as a 30-inch high column of mercury. And the standard atmosphere is also described as about 1,000 millibars. Maybe it's not exactly 1,000, maybe it's 1,006 millibars, but roughly 1,000 millibars. So that's the standard atmosphere, roughly 1,000 millibars or 30 inches of mercury. So we'll start with 3 columns of air molecules from the surface up to 100 miles. And these 3 columns are identical. We don't have all the air molecules in exactly the same place, but the density is roughly the same. We've got very dense air molecules packed in at the bottom. And as we move up in the atmosphere, the packing gets less and less dense. Why is that? Because the air molecules at the surface are being compressed by all the air molecules above them. And they're weighted down, and the air molecule above it is weighted down, and the air molecule above it is weighted down. And eventually, when you get way up in the atmosphere, there's not much to weigh it down anymore. So the air molecules are very spread out. So this is kind of a steady state where all 3 columns of air have roughly the same concentration of molecules at any given altitude. So now let's remove some air molecules from the middle column. So you can see visually here that in this circle, we've only got 3 molecules of air. And if we looked at this circle, the same size circle over here, we would have maybe 10 molecules, and over here we'd have maybe 9 molecules. So there are far fewer air molecules in this green circle. We've removed some. Maybe this is a jet stream where air molecules are moving away from the area and they've been pulled away by the jet stream. And what that's going to support is the movement of all the molecules below where the air was evacuated upward. So these air molecules in here no longer have as many air molecules above them pressing them down, so they're all going to tend to rise. So the air is going to tend to be buoyant in this column of air. All those air molecules are going to tend to be buoyant, tend to rise a little bit. The atmosphere will also try to equalize the concentration of molecules at any given altitude from one column to the next to the next. So the right column and the left column will also contribute molecules to the middle column where there is less concentration of molecules. So we tend to get a motion of air toward the column of air where the air is rising, and we tend to get a motion of air upward in the column of air that's had air molecules removed from above. Now, what do we remember about the latent heat energy cycle when some of this air is moist? That rising air is going to also transport not only air molecules upward, but the water vapor, the latent heat energy with it. So this column of air is going to tend to have rising air molecules and energy moving up in the atmosphere in the form of latent heat energy that could cause thunderstorms and unsettled and potentially nasty weather. So I'm going to prove to you why moist air is lighter than dry air. And that sounds counterintuitive, but it's really straightforward, and we don't have to do any complicated math because I don't like complicated math. So the atmosphere is made up primarily of these four gases. H2O, that's two molecules of hydrogen with a molecular weight of one each, and one molecule of oxygen with a molecular weight of 16. So an H2O molecule is going to have a molecular weight of 18 molecular units. Carbon dioxide is one carbon with a weight of 12 and two oxygens with a weight of 16. CO2, carbon dioxide, one molecule of it has a molecular weight of 44, more than twice as heavy as H2O. Oxygen is O2. That's two oxygens at a weight of 16 for a weight of an oxygen molecule of 32. And nitrogen is N2. That's a molecular weight of 14 each for the two nitrogen molecules, and that creates a molecular weight of 28 for the N2 molecule. So these are the primary gases in the atmosphere. The atmosphere is 75% nitrogen with a weight of 28, 20% oxygen with a weight of 32. It's less than 1% CO2 with a weight of 44, and it's less than 5% water, H2O, with a weight of 18. And if you add those up, that's 75, 95. We've gotten just to right about 100. Anything else in the atmosphere is a trace gas. There's very little of it. So out of those four molecules, which make up basically the whole atmosphere, which is the lightest? H2O, water. So if we have a parcel of air, we've got 50 air molecules we're looking at in a parcel of air. If we want to add H2O, we're going to have to take out another molecule because we're only looking at a parcel of air and it can only hold so many molecules. So if we take this parcel of air and add a couple of H2O molecules and take out a couple of CO2 or O2 or N2, what do we end up with for a total weight of all of our molecules in our parcel? The weight's going to go down. The more water we add, the lighter the parcel of air becomes. So that is completely counterintuitive, isn't it? So why does that matter? Well, remember the latent heat energy cycle. The more moisture we have, the more latent heat there is, the more energy is going to be released when the atmosphere cools as it rises and condenses out to form clouds. The more clouds are going to form, the more that air is going to get forced upward even faster, and we get towering thunderstorms. And we're going to come back to this subject in one of the later seminars. I think it's 201 or 202. We're going to come back to this and explore more about lapse rates and latent energy transfer. But I wanted to introduce it here because it's a really key concept, and it's not that difficult, I think, the way I've explained it. And it's really important to plant the seed now, understand it, and we're going to use this more in later seminars. So why does it matter that air has weight or mass? Air has energy. It's got mass. It's got inertia. It's got momentum. The laws of the conservation of energy tell us that energy can't be created or destroyed. It has to be conserved. We can't make energy out of nothing, and energy doesn't just vanish. It just transforms or moves or does something, but it doesn't just come out of nothing or go away. So air which is not moving will only begin to move when a force is applied to it. It's got inertia and it needs something to get it moving. And air which is moving has momentum and it's going to continue moving at a similar speed in a straight line until a force is applied to cause it to change direction or change speed. So quiz time. A barometer measures temperature, wind, humidity, or the weight of all the molecules in the column of air. Obviously, it's the weight of all the molecules in the column of air. Air has weight or mass. Air has momentum and characteristics of inertia. Air has energy, or all of the above. Answer is all the above. Moist air, air that has lots of water vapor, is heavier than dry air or lighter than dry air. Counterintuitively, moist air is lighter than dry air. Moist air that has a lot of water vapor, does it have more energy than dry air or less energy than dry air? It's got more latent energy, more potential energy. Warm air has more energy than cool air or less energy than cool air? It's got more energy than cool air. Okay. So George asks, if the barometer is rising, then it signals bad weather. Actually, it's exactly the opposite. So the reason is back to this. And again, we're going to get into this in more detail with a couple of other examples in a later seminar. But it's important that you understand the concept here. So in which column of air is the barometer going to be lower? In this column, or this column? Remember that the barometer is only measuring the weight of the molecules above it. So the answer is the middle column is where the barometer is going to be lowest because we've removed some air molecules up in the upper atmosphere, and this column of air is lighter because of it. So a low or falling barometer is consistent with a rising air mass. A rising air mass transports energy up in the atmosphere where latent heat energy in the form of water vapor can be released and form clouds and squalls and thunderstorms and all sorts of havoc. So a low or falling barometer is a sign of bad weather. A high or rising barometer is generally a sign of settled, stable weather and pretty high confidence in the forecast details. Okay. And now we'll move into the third module, and I just start this by talking about wind direction. And we're going to talk about convergence and divergence, and then some global energy transfer stuff, and then we'll wrap it up for tonight. So when we say that the wind is north, when there's a north wind, what do we mean? Do we mean that the air is blowing from the north or blowing to the north? Well, the wind is always defined as the direction that it is blowing from. So a north wind is blowing from the north toward the south. A southwest wind is blowing from the southwest toward the northeast. So if we look on a weather chart where we've got wind flags, the half wind barb is 5 knots. The full wind barb is 10 knots. So this wind is 10, 20, and 5. And the wind always points toward the end of the stalk. So this is a southwest wind blowing from the southwest at 25 knots. This is a northeast wind. It's blowing from where the wind flags are toward the base of the stalk and it's a full flag, so that's 10 knots. This is south at 5, and this is north at 75. So the filled in triangle is 50, 60, 70, and 5. So 75 knots blowing from the north. Now, an interesting aside is that when we talk about sea surface currents is one parameter that's exactly the opposite. So when we talk about sea surface currents, we talk about where they are flowing to. So the Gulf Stream off of Florida is a north flowing Gulf Stream. So that's interesting to appreciate that's the only example I can think of in meteorology where we talk about where we refer to the direction as where it's going to. So sea surface currents are different from wind in terms of the direction. Let's talk about convergence and divergence. And this comes into play in this graphic as well. And this will come into play a lot in Module 102 that we'll do next week when we talk about upper air effects. So air which is coming together is termed convergence or converging air. Airflow which is moving apart is called divergence or diverging air. So you can see obviously that these air molecules and these air molecules are converging exactly on one point in the middle of them. That's convergence. That's pretty obvious. And this is divergence. Air molecules going in one direction and air molecules going in exactly the opposite direction. That's obviously divergence. But it's also important to understand that there are two other ways to think about convergence and divergence. So air molecules that have some component of motion towards each other are converging. They're not directly towards each other, but there's some component of motion towards each other, and that's convergence. And air molecules that have some component of motion away from each other is divergence. There's also speed convergence. So air molecules out in front moving slowly, air molecules coming up from behind moving more quickly. That creates a speed convergence as the air molecules from behind catch up with the air molecules in front. And this is divergence. The air molecules out in front are moving away faster than the air molecules behind are moving more slowly. That creates a divergence. And generally, the reason this is important is convergence tends to support lift in the atmosphere. It forces air upwards. And we just made the case for why forcing air upwards is bad. It creates inclement weather. And air that is divergent tends to support a sinking air mass and relatively stable, settled weather. In Weather 102, we're going to talk about this, but I'll introduce it now. Convergence and divergence are very important in understanding the surface effects of upper air weather. And if we get converging air at the surface, air molecules colliding with each other at the surface along a boundary, that's going to force air upwards in the atmosphere. And if at the same time in that same area, in the upper atmosphere, we get air that's diverging, moving away from each other in the upper atmosphere, that creates a sucking, pulling up from below. So here we have surface convergence forcing air upward, and we have upper divergence sucking air upward. So this is, again, a push-pull, and it amplifies the rising motion of the air. So this is a key concept in understanding upper air influence on the surface. Oh, and so little quiz here, and then we'll get into the last part. So wind flags describe the wind direction, the wind speed, or both. Wind flags give us the direction and the speed, both. This image describes what direction and speed. Is that southwest at 25? Is that east at 12? Northeast at 25? Northeast at 15? Or southwest at 15? That's northeast at 15. It's blowing toward the base of the stalk. So it's blowing from the northeast toward the southwest. So it's a northeasterly wind. And it's 15 knots, 10 and 5. Convergence and divergence tell us about the net motion of air molecules toward or away from each other. Is that true or false? And that's true. Convergence describes air molecules which are moving directly toward each other, which have some component of speed or direction of motion toward each other. Or does convergence talk about air moving away from each other, or have some component of speed or direction moving away from each other? Or are A and B or C and D the most correct? The answer is A and B are most correct. Convergence is either air moving directly toward each other, or at least with some component of direction or speed toward each other. Convergence. Divergence, same phrasing, is that air moving directly towards each other, having some component of motion or speed towards each other? Or is it directly away from each other or some component of motion away from each other? Or is it A and B or C and D? In this case, divergence is C and D. It's either air molecules moving directly away from each other or some component of either speed or direction away from each other. Okay. And last topic for tonight. So, John, the intertropical convergence zone, why is it mostly from the equator to 10 north? So it does shift around a little bit, but it, for various reasons, one of which is there's more landmass in the northern hemisphere. The ITCZ is offset slightly from the equator. So the mean position of the ITCZ is probably 5 degrees north latitude. In our summer, it's often 15 degrees north latitude. And it kind of averages, somewhere between the equator and 10 north. In our winter, when the southern hemisphere is having summer, it's maybe at 5 or 10 degrees south latitude. So the average position is just a little bit north of the equator. The average position is probably about 5 degrees north of the equator. And the range is from about 15 north to around maybe 7 or 8 or 10 south. And I should make it more clear that the intertropical convergence zone is a zone. It's not an exact line. There tends to be a northern boundary and a southern boundary, and the whole zone shifts north and south. And the ITCZ, sometimes it's narrow, sometimes it's only a couple of degrees of latitude in breadth, and sometimes it's quite broad, 5 or 10 or 15 degrees of latitude in breadth. But the mean position is a little bit north of the equator. So now we're going to talk about energy transfer on a really large scale. And this will wrap things up for tonight. So you might expect that there is just one cell that moves unevenly heated air from the equator to the poles and the poles back to the equator. So think of the air at the equator. It's really warm, it's really moist, it's in a really high energy state. The atmosphere really hates that and really wants to make things equal. So the air that's over the North Pole and the South Pole is very cold and very dry and in a very low energy state. And the atmosphere hates that there's that difference. So it's trying to make the atmosphere more uniform. So there is a mechanism that transports the warm, moist air toward the North Pole and toward the South Pole, and the cold, dry air from the poles back toward the equator. Read about that more. This is a really simplistic model and not real world. The complication is that there's the Coriolis effect. The Earth is spinning, and that spinning induces a turn. So as this air is trying to move from the equator to the North Pole, it gets curved because of the curvature of the Earth and the rotation of the Earth. And the air that thinks it's going a straight line is actually making a curve because of the Earth turning. And so this creates a number of cells in the globe. And there are three primary cells. So here we have the intertropical convergence zone near the equator, and that tends to be an area of persistently lower pressure. And then near the North and the South Pole, there tends to be an area of persistently high pressure. And between the two, there's another high and another low. So in the subtropics, around 30 degrees north latitude, give or take, we have an area of relatively persistent high pressure. And up around 50, 60 degrees north latitude, we have an area of relatively persistent low pressure, or at least migratory areas of low pressure that come through, low pressure systems, cold fronts, things like that. So in actuality, we get air rising at the surface, rising from the surface over the equator, and then sinking back under high pressure around 30 degrees north latitude. Some of that returns toward the equator, some goes toward the North Pole. That tends to rise in the atmosphere in areas of low pressure up near 50 or 60 north latitude. Some of that goes back toward the equator, some goes toward the North Pole. And then air over the North Pole tends to sink, and that's high pressure. So it's a circuitous route. The rising air at the equator that's trying to get to the pole has to go up and up and finally down. This creates I added a little bit of graphics here to define some of the latitudes. So in the tropics, that's from the equator to roughly 23 degrees north and south. And that's where we tend to have relatively persistent areas of lower pressure. And in the subtropics, we have ridging. We tend to have areas of relatively higher pressure. In the subtropics between, say, 23 and 35 north. Now, this changes in winter versus summer. So in summer, the ridging may go north to 40 or 45 north. But it's not as far south in the southern hemisphere during their winter. And then, in the wintertime, this all gets forced southward in the northern hemisphere. And between 35 and 66 north, we tend to have migratory areas of low pressure coming through. There are also migratory areas of high pressure, but the weather is really dominated by the lower pressure, generally between 35 and 66 north latitude. And then north of 66 north, we have the polar high. We just described this, but this just reiterates the circuitous flow of air from the equator to the poles and back again. So this is a really neat graphic from the European Met Office. This is the mean annual average wind. And the scale here is in meters per second. So it's about 2 knots per meter per second. So the yellow shading, that's 2 to 4, that's 2 to 4 meters per second. That's about 4 to 8 knots. And the areas shaded in green are 4 to 6. That's about 8 to 12 knots. And we don't really have any areas shaded in purple or magenta. We only have 3 shadings here. So it's 2 to 4, 4 to 6, or 6 to 8. I guess there's an 8 to 10. Yeah, this deep blue here is 8 to 10. And it's kind of hard to see, but these little black dashes actually are wind arrows. So that denotes the wind direction as well as the shaded area denoting the wind speed. So here's the United States, and we kind of know the latitudes around the United States. The Florida-Georgia border is about 30 degrees north latitude. So that radicule there, that hash line, is 30 degrees north latitude. What do we notice for a mean annual average wind near 30 degrees north latitude? It's 0, or it's less than 2. So it's essentially 0. Why is that? Well, that's because there's a persistent ridge of high pressure near about 30 degrees north latitude. Which way does air rotate around an area of high pressure in the northern hemisphere? Clockwise. We'll talk more about this in our next session on Thursday night. But air rotates around high pressure in a clockwise fashion in the northern hemisphere. What do we notice about the wind north and south of 30 degrees north latitude? It's really hard to see, but if you could see the arrows on the end of these little dashed lines, all the arrows in this yellow area and this green area between the US East Coast, north of Bermuda, all the way to the United Kingdom are blowing out of the southwest and out of the west, southwest, and west. So the mean annual average wind direction is west, southwest to west between the US coast and England. So why did sailing ships ply the waters north of Bermuda, near and north of the Azores to get to the UK? Because it was downwind. Same reason we sail that way today, because it's downwind. Now, it's not always downwind, but more often than not, it's downwind because the wind is doing this great big clockwise circle across the Atlantic. So what do we see off of the Iberian Peninsula, off of Portugal and Spain and northwestern Africa? Those arrows are pointed south. It's really tough to see, but if you could see the direction of those arrows are pointed, that's from north to south. So that's a north wind blowing along the Iberian Peninsula, between the Iberian Peninsula and the Azores. And then from the Canaries to the Caribbean, it's a little easier to see those arrows because they're bigger lines because they're faster wind speed. And those are blowing from the northeast near the Canaries to the east-northeast as we cross the Atlantic and almost east as we get into the Caribbean. So that creates a really nice clockwise flow. It's kind of elongated, but it's a nice elongated clockwise flow around that subtropical ridge of high pressure. So that's kind of cool, isn't it? We just learned why we sail the way we sail, the direction we sail, because of the large scale weather pattern. And we understand why that happens. We also understand why, unless we're a trawler and we're looking for no wind, we want to kind of avoid sailing along the ridge of high pressure because there's no wind there. So going to Europe, we want to be north of the area of high pressure. Coming back from Europe, we want to be south of the area of high pressure. So what happens in the southern hemisphere? So the equator is right here. And we tend to have a convergence. Notice that in the southern Atlantic, the wind is counterclockwise because high pressure goes the other way in the southern hemisphere. So we've got air blowing from west to east from the southern tip of South America to the southern tip of Africa. That's blowing from the west to the east. And then air turns north, then northwest around the subtropical ridge of high pressure at about 30 south latitude in the southern hemisphere. So we've got air moving northwest, then west-northwest approaching the equator from the southern Atlantic. And we've got air flowing from the northeast to the east-northeast, east-northeast, and then east from the northern hemisphere. So you can see quite clearly that these air patterns are converging. And what do we know about convergence? Convergence forces lift. Lift creates squalls, thunderstorms, clouds. That's what makes the intertropical convergence zone tick, is the convergence of the northern hemisphere winds, which have some north component of motion, and the southern hemisphere winds, which have some component of motion from the south, converging on each other around about the equator, and that helps create all that unsettled weather at the equator. One final note on this graphic. I love this graphic. Notice how overall there's much more yellow shading in the north hemisphere and a little bit of greens. And in the southern hemisphere, there's a lot more green and even some blue, which is really strong wind, and very little yellow. So why is that? Well, by far, there's more land mass in the northern hemisphere, which creates more friction and it slows the wind down. And in the southern hemisphere, there's very little land mass, especially in the deep southern hemisphere, south of 45 degrees south latitude. There's very little land mass. Really only southern tip of South America sticks down, between 45 and 60 degrees south latitude. And that's not a very big landmass. So the air really gets roaring, hence the name of the roaring 40s and 50s in the southern hemisphere. So you can read through these. They're kind of self-explanatory. We talked about all the all the major things dealing with each of these zones and their characteristics. Just a couple of final points I'll make. We often talk about a polar front, and this is really important along the US East Coast in the summer, and it's important if you're in the Bahamas and Florida in the winter. It's where there's a tendency for approaching cold fronts to stall. So it's the boundary between the warm, moist tropical air mass to the south and the cool or really cold Arctic air mass to the north. The Arctic air mass in the summer is not very cold in the northern hemisphere, but it's still quite a bit cooler than the warm tropical moisture air mass. So where those air masses clash, we get a lot of really active weather, really strong, really squally cold fronts, really strong areas of low pressure, and really, really bad weather. And that tends to follow the low pressure systems that are migratory in the area. We get a low maybe coming through once or twice a week. And that area of low pressure is going to tend to follow a track that is along the polar front. And the polar front is then pulled north and south. So typically, as an area of low pressure comes through, it pulls the polar front north of where it was preceding the low. So let's say we have a low that's moving over Oklahoma, and we've got a cold front that's stalled along the Carolinas, and that's the polar front. As that low moves from Oklahoma across the Mississippi Valley into the Carolinas, it will pull that frontal boundary that's kind of stalled along the Carolinas northward, maybe up to the Chesapeake Bay as a warm front. And then after the low passes, it'll pull that frontal boundary south again as a cold front, back down to the Carolinas or maybe even into Florida. And this frontal boundary, that's the persistent differentiation of the air masses, tends to just shift around. Often it'll be dislodged. So if a really strong low pressure system and cold front come through, it may push the front hundreds of miles further south of where it's been for the last month. But unless it's a really strong low and a really strong cold front, it will tend to gravitate back to where it's gravitated before. So it'll press south as a cold front behind a low and lift north as a warm front ahead of the low, and it'll just kind of go back and forth. And there's a lot of really active weather along that. So when you're heading north and south in the fall, you're heading south probably, and in the spring, you're heading north probably from the Caribbean or the Bahamas. There are three zones. There's, of course, the equator and the weather that's south of the ridge of high pressure. And then there's the subtropical ridge of high pressure. And then there's the area that's in the path of the migratory lows and cold fronts and warm fronts and nasty weather. So the key is, if there's one secret to moving north and south to and from the Bahamas and the Caribbean, it's spend as little time in zone 3 as possible. Use whatever wind there is in zone 3 to the best advantage, because you don't want to get to zone 2 and then have to motor 500 miles in no wind. But if you're headed to the Caribbean from the US East Coast, you definitely want to make all your easting before you get into the easterly trade winds in zone 1. So you time your departure in zone 3. Let's say you're leaving from Newport or from the Chesapeake or from Beaufort, you're in zone 3. You're in the path of the low pressure systems and the cold fronts and the really nasty weather. You're going to leave at a time that gives you sufficient time to get the heck out of zone 3 before the next gale. And you're going to use the wind you've got to try to position yourself so that you have to do as little motoring as possible in zone 2 before you get to the nice sailing and set yourself up in the right place to enter zone 1 so that you get good sailing down to the Caribbean. So that's in a nutshell how all of this comes together for planning voyages to and from the Caribbean. I'm going
Chris,
to just make a note that if you're interested in proving to yourself why the Coriolis effect works and how it works, there are slides here at the end that have really in-depth discussions, and I prove to you why the Coriolis effect works and the effects that it has. So read through those. It'll take half an hour to read through them. But read through those, understand them, and you'll come away with understanding exactly why the Coriolis effect works, why the Great Circle routes work for sailing. And, we won't take time to do that here.
Well, Chris, this is really, I know that everyone who's been staying in there, because we still have over 100 people here listening. That's a pretty good number of mariners, I think, or people
Yep.
interested in weather. So it is almost 9 o'clock, Chris.
Yep.
It's late
So
for you.
that's it for tonight.
Yep. And we will see you on Thursday at 7 p.m.
Okay.
And I want to
And
thank everyone.
let's see, were there any questions we didn't answer? Um,
I think you answered Krista, and then Hector had one, and then we had an anonymous attendee. What causes air to converge or diverge? And I think you did that.
yep.
Hector's question, out in the ocean, far from land, do you also have a daily weather cycle? And
So I didn't see that question. So away from land, is there a daily weather cycle? Yes, there often is. And we'll talk about this some in some of the later modules. Particularly in the tropical marine environment, we tend to get more wind and more squalls and thunderstorms at night. And I'll explain why that is in some of the later modules. In the northern hemisphere, it's not as significant away from land. But there tends to be a backing and veering pattern to the wind. So the wind tends to back maybe 10 or 20 degrees around sunset. If you're in the Caribbean and you're a keen weather observer, you've seen this. The 5, 6, 7 o'clock in the afternoon, the wind all of a sudden backs by 10 or 20 degrees and increases by 2 or 3 or 4 or 5 knots. And it remains kind of elevated and from that direction most of the night. And then the following day, it gradually veers that 10 or 20 degrees and drops. We also tend to see more squall and thunderstorm activity at night in the tropical marine environment. And I can explain why those happen. But yeah, away from the area, away from land masses, there doesn't tend to be a lot of daytime, nighttime differences in northern latitudes, but there does tend to be in southern latitudes. And thanks for sharing the information on the pilot charts. So John Owen, a relationship between highs and lows and warm fronts and cold fronts, that's a topic that we're going to address on Thursday. So that's the next session. That's Weather 101. This was introducing everything to you so that you're going to understand Weather 101 when we get there on Thursday. Without what we did tonight, you wouldn't, Weather 101 wouldn't be very clear. But now you'll get Weather 101 when we get to it on Thursday. Okay. And Jay, my secret to explaining things clearly is that I'm not very smart and I don't have a deep science or math background, but I understand the basic concepts. And if you're of average intelligence like I am, then I can explain it to you. But my secret is that I'm not that smart, and I didn't do very well in math and science, or at least the high level math and research meteorology in college. So I think that's actually a benefit, not a drawback, in terms of being able to explain it. All right. Well, everyone have a good night.
thank you very much, Chris. We will see you on Thursday. Have a good evening, and thank you very much, everyone. We have another question here. Another question on the video. Yes, the video will be made available via a link to YouTube, so everybody will be able to see it, and the slides will be available to read in a PDF format. Correct, Chris? I can send them that.
So anyone who subscribes to the whole course gets
Okay,
the PDF, but anyone can view it on YouTube. So if you
right.
missed anything tonight, it'll be free on YouTube for everyone.
Okay, very good. Thank you very much, Chris. We will see you next. Oh, we got more questions here. Um, the next session will be about the same, Walter. And the video will be ready about tomorrow. It has to process tonight.
Yeah, the next session is probably a little shorter. The sessions are between an hour and, hour and a half, hour and 45 minutes. This one went almost 2 hours. Most of the sessions are more like between an hour and a half.
Okay. Thank you very much, Chris. Have a good evening.
All
See
right.
you all later.
Good
Thank
night.
you all very much.